A special type of sequence is a recurrence relation. So a recurrence relation for sequence AN is an equation that expresses AN in terms of one or more of its previous terms. In other words, instead of saying what AN is explicitly, what the nth term is explicitly, we are going to define it in terms of some previous terms. So we are going to have the sequence as A0, A1 up to AN minus 1 for all integers n greater than n0, where n0 is some non-negative integer. A sequence is called a solution for the recurrence relation if its term satisfies the recurrence relation. In other words, if you wanted to find a term in a sequence that is specified in terms of a recurrence relation, I will have to find all the previous terms in order to find the current term. A solution will allow us to identify that term quickly by just plugging in the value of n in that sequence. The initial conditions for a sequence specify first few terms in the sequence before the recurrence relation takes into effect. Let's look at an example for recurrence relation. So here I have the sequence AN that satisfies the following equation. AN is AN minus 1 plus 3 for n is equal to 1, 2, 3, 4 and so on. And the initial value A0 is 2. So let's ask the question, what is A1, A2, A3? Pause here if you want to do this work by yourself. It's fairly straightforward. In this sequence, we call A0 equal to 2 as the initial condition. And now we can see that A1 is A0 plus 3, so that will make it 5. A2 is 8 and so on and so forth. So now what we have here is a sequence that is specified in terms of a recurrence, whereas if I wanted to find this without going through the recurrence, I would need to come up with some sort of a solution. In this case, the solution would be 3n plus 2, and that is what we will call the solution to this recurrence relation. Now this example is fairly straightforward. Finding the recurrence relation is straightforward. One of the things we are going to study not immediately but a little later is how we can do this systematically. Here is another example. Here I have AN is A of n minus 1 minus A of n minus 2. And now here the recurrence relation talks about two previous terms, so I need to define two initial terms so that I can keep finding subsequent terms. So here A0 is 3, A1 is 5. So question is, what is A2, A3, A4, etc. Once again, pause here if you want to work this out yourself. Now what we can see is A2 is A1 minus A0, in this case it's 2. A3 is A2 minus A1, that will be minus 3 and so on. Fibonacci sequence is a special type of sequence where the term F0 is 0, the next term is 1, and the remaining terms are identified by the recurrence relation Fn is equal to f of n minus 1 plus f of n minus 2. So our goal is to find f2, f3, f4, f5 and so on, and what we can see is f2 is going to be 1, f3 is going to be 2, and the next terms are going to be 3, 5, 8 and so on. Now if you recall, earlier when we talked about just defining sequences, I had a formula that described a sequence, and it turned out that the numbers it identifies were exactly the same as the Fibonacci sequence. So a closed form solution is basically start from this sort of a recurrence relation that we have over here and come up with a solution like what we had on the earlier slide, where instead of having to find all intermediate terms, I can find, say, the 100th term automatically by plugging in n is equal to 100 in that equation. So solving recurrence relation is finding a formula for the nth term in the sequence generated by that recurrence relation. So if I wanted to find nth term using the recurrence relation itself, I will need to know what is the n minus 1th term, n minus 2nd term, and so on. A solution, on the other hand, will simply allow me to plug the value of n rather than having to find all previous values. Such a formula is what we call closed formula. So there are lots of different ways we can solve a recurrence relation. We will study this in more depth in chapter 8. But right now what we will do is we will look at some patterns to figure out what the closed form formula is likely to be. So one method to do this is by doing forward substitution. So here I have an is an minus 1 plus 3. So I can write a2 is equal to 2 plus 3, a3 is equal to 2 plus 3. This is what I had before, plus 3. So I can write this as 2 plus 3 times 2. The next one is 2 plus 2 times 3 plus 3, that is 2 plus 3 times 3. And so I can see that there is some sort of a pattern going on here. I have a 2 plus something, and then here what I have is 3 times something, and this term that I have here is 1 less than the number for which I'm finding the term. So for the fourth term this number is 3, for the third term this number is 2, and so on. So now I can use this to figure out that for the nth term I'm going to get 2 plus 3 times n minus 2 plus 3, which is 2 plus 3 times n minus 1. Once again, this is basically just trial and error. We will study more systematic ways to do this in chapter 8. We can do the same thing working backward. So here I have an is equal to an minus 1 plus 3. So I can substitute an minus 1 as an minus 2 plus 3. Note that what I'm doing is I'm replacing this term by this term, which is something that I'm allowed to do by the recurrence relation. This plus 3 is left as is over here. So now I can see that this is an minus 2 plus 3 times 2. I can continue further. I'll get an minus 3 plus 3 times 3. I keep going. I will get the formula 2 plus 3 times n minus 1. Here is an application of the recurrence relation. Suppose a person deposits $10,000 in a bank, yielding 11% per year. How much interest would be accumulated over 30 years? So here we can write Pn as the amount of money after n years. We can write a recurrence relation relating Pn and Pn minus 1, which is going to be Pn is whatever was there in the year before plus 11% of whatever was in there before. So that's 1.11 times p of n minus 1. The initial condition would be P0 is equal to 10,000 because that's what we started with. So now we have this recurrence relation. We can do forward substitution. So we can see P1 is 1.11 times P0, P2 is 1.11 times P1, which is 1.11 square times P0. And we can continue, and we will see that Pn is 1.11 times 1.11 to the power n times 10,000. We can prove this by induction. This is something we will study later. And now we can put n is equal to 30 to get the answer that we want. In this case, it is 228,992.97. Once again, we have reached the check before you go ahead slide. I want you to find the terms A2, A3, A4 for the sequence that is specified as follows. Again, the answers are at the bottom, so if they don't match with what you get, then please check with us. At this point, we have reached the end of this module, so I want you to do the review quiz. A couple of things I want to mention here is this module only looks at the basics of recurrence relation. We focus on how to solve the recurrence relation in module 42. Those of you who are interested in the topic can go ahead, jump to it. Some things may not be exactly clear because it depends on some parts of module 40 and 41, but most of it should be interesting to follow.